In the silent halls of logic, where numbers and sets follow strict rules, a profound question echoed unanswered. By the mid-20th century, the Continuum Hypothesis, roughly asking if any infinity lies strictly between that of the whole numbers and that of the real numbers, remained an urgent puzzle. Cantor had shown the real numbers form a larger infinity than the integers, but whether any intermediate size existed was unknown. Imagine an infinite mountain with two visible peaks and a hidden valley in between. Could it exist? No one knew. For decades, mathematicians believed its resolution was inevitable. For skeptics, it was a test of mathematical certainty, and still, the answer eluded them. It seemed a secret hidden in the very nature of infinity, teasing the limits of reason. Most mathematicians assumed every well-posed question could be settled by logical proof. But what if that assumption was flawed? For years, the Continuum Hypothesis was like a distant mountain, visible but obscured by clouds, awaiting a solution that would quietly reframe how mathematics understands truth.
A bit about what I got interested in set theory. These stories, for example, did you say, oh, maybe true, but that some people came up to me and essentially said that story in a slightly different form. And we were talking about truth. And I said, what does it matter when the story is true? You're going to continue to tell it, aren't you?
Paul Joseph Cohen was born in April 1934 in Long Branch, New Jersey, to a Jewish immigrant family. His brilliance was evident from a young age. At 9, he devoured a calculus book, astonishing librarians. He excelled at Stuyvesant High School and won prizes in mathematics competitions. At 16, he entered Brooklyn College and quickly realized he could accelerate his studies. By 19, he began graduate studies at the University of Chicago, earning a Ph.D. in 1958 under Antony Zygmund, a teenager mastering calculus before many adults. What drives a mind like this? Cohen thrived in the golden age of analysis, attending lectures by some of the century's leading mathematicians. He held research positions at the University of Rochester, MIT, and Princeton's Institute for Advanced Study before joining Stanford University's faculty in 1961, where he would teach for nearly 50 years. Even early on, Cohen was drawn less to calculation than to structure and logic. He sought understanding of why results must exist, rather than the results themselves. Students and colleagues recall him as patient, clear, and exceptionally broad in his interests. Outside mathematics, he played piano and violin and sang in Stanford's chorus. Could a musician and a mathematician live in the same mind? Cohen proved it could. In the late 1950s and early 1960s, Cohen made significant contributions to analysis, solving complex problems and proving elegant results, such as the Cohen idempotent measure theorem. He received the Boscher Prize in 1964 and was recognized internationally, speaking at major conferences and winning a Guggenheim Fellowship in 1963. Yet his mind was drawn to a deeper challenge, the foundations of mathematics itself. The Continuum Hypothesis had long been a beacon of unresolved inquiry. In 1940, Kurt Gödel had shown CH could not be disproved from the standard Zermelo-Frankel axioms. But whether it could be proved remained open. Many assumed it was hopeless. Cohen was prepared to challenge that assumption. What if the rules you've always trusted are incomplete? Could you prove it? In 1963, Cohen devised a daring new method called forcing. Forcing allows one to expand a mathematical universe in a controlled way, constructing new sets that extend a model while preserving its consistency. Using forcing, Cohen built models in which the Continuum Hypothesis fails, yet all axioms of Zermelo-Frankel set theory remain true. He applied the same method to the Axiom of Choice, showing it too is independent of ZF. Cohen had shown that from ZF alone, neither CH nor AC can be decided. This was a revolutionary insight. It meant there is no single definitive universe of sets, only many consistent ones. Mathematicians now saw that some questions about infinity have no answer within the old framework. The landscape of mathematical truth had expanded. Imagine opening a door in mathematics and finding not one universe, but an infinite gallery of them. Cohen's peers immediately recognized the magnitude of his work. It was compared to Gödel's incompleteness results, transforming the understanding of foundational mathematics. In 1966, at the International Congress of Mathematicians in Moscow, Cohen was awarded the Fields Medal for his independence proofs of the Continuum Hypothesis and the Axiom of Choice. For Cohen, the medal was a symbol. It signified a logical revolution had taken place, a shift in perspective that would influence generations of mathematicians. But the real reward was the new ways of thinking his work had opened. A Fields Medal for proving a question has no answer. What kind of achievement is that? After his breakthroughs, Cohen continued teaching and researching at Stanford. He guided generations of students and published influential works, including Set Theory and the Continuum Hypothesis, and Set Theory, an Introduction to Independence Proofs. His methods became standard in set theory. Forcing is now taught as a foundational technique. His influence extended beyond logic. He demonstrated that axioms are assumptions we choose, that the infinite can branch into multiple coherent worlds, and that mathematics is as much about framing questions as finding answers. What if the rules of your universe were only suggestions? Cohen showed us they could be. Decades later, Cohen's approach continues to inspire mathematicians to explore new frontiers and question long-held assumptions. His life reflects curiosity, intellectual courage, and a commitment to clarity and rigor. Paul Cohen passed away in 2007, leaving behind a legacy that reshaped how we understand infinity, logic, and the very structure of mathematics. His work reminds us that some questions do not have answers in the old framework, and that choosing new axioms can open entirely new horizons. The infinite is not one, but many, and Cohen handed us the map. This is Awards, where the world's greatest minds live forever. Don't just watch history, be inspired by it.